Okay, we're going to take a look at some advanced bonding theories for the end of for chapter 8. I'm not going to go into all of it. There's going to be MO diagrams and a bunch of other stuff as well. But generally, I'm just going to focus on VB theory. So let's talk about this. So we have drawn Lewis structures. We've talked about what a covalent bond is, but we haven't really gotten into theories about how bonding actually works. So we're going to start with the idea of valence bonding theory. So the bond between two atoms is the result of overlap of their atomic orbitals. So for valence bond theory, again, interaction between two atoms, and we're always going to start with, we have an s orbital, and where the whole wave function is positive, and the p orbital where you have plus and minus. So these are the two that we're going to start with. So there's two interactions that you could essentially have. Positive would result in a constructive interference, and that would be a bonding situation, and negative and positive would result in a anti-bonding, where bonding would not happen. It would create a node because they would cancel out. It would be destructive interference. So example 8.1. How is the covalent bond formed between two hydrogen atoms? So the simplest one, we're going to always start with the Lewis structure. How do those two things bond? So how does the atom hold together? Let's draw the energy diagram and indicate the bond length. And we've actually already seen this, so I'm going to go through this relatively quickly. So if we take a look at how does the bond hold together? So we've already talked about how these things actually hold together. So if I have the two nuclei of the hydrogen, there's hydrogen 1, there's hydrogen 2. We know that these are positively charged. And I have these electrons in between them. We know that we're going to have attractive forces holding them together. And then we're going to have these repulsive forces that are going to keep them apart. Okay. And so as long as the attractive forces outweigh the repulsive forces, we have a bond. So repulsive. Oh, can't even spell. There we go. Repulsive, and the dashed lines are attractive forces. Okay, so that is A. Those are how the things hold together. We have attractive and repulsive forces. The attractive forces outweigh the repulsive forces, and we've created an interaction, or we've created a bond. So the energy diagram that I'm interested in talking about, if I have, again, energy on the y-axis, and I have distance, the distance between nuclei and, let's say, picometers on the x-axis. So distance, I guess, of nuclear separation. We're going to run into the situation where we have this little trough, and then it kind of evens out. So over here, again, where we have a reasonable energy, the two hydrogen atoms are very far apart. And as we bring these two things closer together, okay, we are going to run into a situation where the energy starts to dip, because the attractive forces between the electrons that they have are starting to take shape. So bringing these closer together, they're starting to find the electrons of their neighbor. And eventually, at this minimum here, we have the perfect overlap that results in a bond for these hydrogens. So this overlap right here is where that bond is happening. And again, this right here would be the ideal distance or a bond length. And this could be done with any two nuclei. So the bond length of a hydrogen-hydrogen bond. If we keep bringing these things closer and closer together, the nuclei are going to overlap to the point where the energy just skyrockets, because the nuclei are way too close together. So that's what's going on. They're just too close here. and that's why the repulsive forces are right here are just overwhelming all of the attractive forces, and that's why you see that leap in energy. All right, so we noticed that we have that overlap, and that's kind of the most important thing that we're going to talk about for VB theory. So let's talk about interacting two hydrogens. So I have a hydrogen. It is the 1s orbital. There we go. And it has one electron in it. There's my one electron with spin up. This is the 1s with one electron, plus another hydrogen. Again, it's got that spin up electron as well. And it is also 1s. So when I overlap these two things, so when I take this and I overlap it, okay, essentially what we're going to have is we're going to create a bond, and we are going to create a bond between the two of those. There we go. Where they share the electrons in between the two of them. There's the nuclei of the two. Is a little offset, but that's fine. This indicates the overlap of the 1s orbital. Again, this is where the bonding is occurring. Okay, so when you have constructive reinforcement, when they overlap in a positive way, you have a bond form. And of course, what that really looks like when we combine those two wave functions, now I have the two nuclei, and I have reinforcement with those electrons in that cloud in between them. So this is my two electrons in the bond. Easy enough. That's how we do it. I mean, that's the essential of the idea is we're just going to overlap what bonding that we actually have. So why would a bond between two helium atoms, explain why a bond between two helium atoms cannot be formed in the same way. So I will let you explain this and we'll look at it in class. So there's my 1s for helium. And there's my other 1s for helium. Why can I not form a bond there? Let's take a look at fluorine. Let's take a look at the covalent bond between two fluorine atoms. So let's draw out the electron configuration of fluorine, just the valence electron. There's my 2s, my 2p. There we go. There's my 2p electrons. So what we see is these first handful right here, that cannot bond, that cannot bond, that cannot bond. But we do have this with this last p here that can bond because it has just the one electron, it's ready to create a bond. This orbital, we're going to call this the px. So it is, it faces the x direction. So here's my positive, negative. There's my first fluorine. This is the px orbital. Okay. And so if I bring another fluorine in, negative, positive, because I do want the overlap to happen, and you can rearrange those as you wish. When I bring this together, we're going to have overlap here. And we're going to be able to create that bond. One electrons, two electrons. Again, this is overlap is positive, resulting in the bond between the two of them. So again, the positive and negative are constructive versus destructive interference. So if I have two of the same wave functions or two positive wave functions, they're going to reinforce. If I have wave functions that are opposite, you're going to have destructive interference. When this happens, you form a node. Essentially, there's no electron density there because it's canceled out. So now that we have the px and the px, how would you expect a bond to form between a hydrogen and a fluorine atom? So why don't you give that one a go and see if you can come up with it. How about this one? How should the covalent bond be formed between two hydrogens and one sulfur? So again, we're going to start with the sulfur. Here's my sulfur. This is going to be 3s. 1, 2, 3, 3p. 1, 2, 3, 4. So I've got two potential bonding sites. So we'll call this the px. Again, this is the px. This is the py. So we're going to have interaction between the px and the py. So I have two p orbitals that can actually bond. So let's draw those in. So here's my sulfur atom. That is my px. There's my py. So px, py. And now if I bring in my hydrogen atom, which is a positive wave function, let's say. Yeah, it's a positive wave function. There's my hydrogen. So if I bring that in, that can overlap with this one, and we're going to have some bonding. Okay. And the same thing for the other one. We're going to have overlap up here. There's my hydrogen that's going to overlap, and we have bonding. So my question again is, if this is the py and this is the px, if we bond it this way using VB theory, what is the angle I'm expecting? For that HSH, well, it's actually going to be 90 degrees, right? Because those are perpendicular to one another. So if that bond is 90 degrees, we should see that in actually looking at the material that we have. What we find out is, experimentally, we find out that the bond angle equals less than 109.5 degrees. So it's not 90, it's close to a tetrahedron. So again, VSEPR indicates the angle is different, and this is problematic. So VSEPR is telling us the limitations of valence bond theory is we can use these orbitals to see things, but the angles are not going to be right. And so there's something going on here that we need kind of clarification on. So VSEPR indicates different stuff. I guess technically that's a bonding theory. So VSEPR shows different angles, and actually more correct angles than this one does. So there is some proper situation that we have to look at. And so that's where we come up with the idea of hybrid orbitals. Hybrid orbitals is we're going to be mixing different orbital types together and to kind of taking the average of what they all kind of look like. So first of all, the most important thing about this is the number of hybrid orbitals equals the number of atomic orbitals that are mixed. So number of atomic orbitals equals number of hybrid orbitals. So when we combine some orbitals, make sure that you have the same coming out. So let's take a look at what happens when I create these hybrid orbitals. So overlap of 1s and 1p. So here's my p orbital. We'll go back to the, well, it actually doesn't really matter, positive and negative. If I overlay a s orbital on top of it, okay, what does that actually look like? So I guess I should say this instead. So there's my s and my p. I'm combining my s and my p. So an s plus a p orbital. What is the combination of those two orbitals? So first of all, if I have two orbitals that I'm combining, two atomic orbitals, how many hybrid orbitals should I get? Well, 2 in, 2 out. We should get 2 hybrid orbitals out, okay? So when we take a look at this, what we're going to see is right here, I'm going to see constructive interference. Constructive interference, meaning those two are going to reinforce one another because I have the positive S and the, again, this is positive, this is positive. So positive and positive, those combine to give us constructive interference. Over here, however, we're going to have destructive interference. That's a little too close in color. Over here, we're going to have destructive interference, and those sections are going to essentially cancel each other out, destructive interference, okay? So the end result of this is when you have constructive interference, they're going to reinforce one another, and you end up with it's actually a little more pronounced than that. There's the negative and there's the positive. So it's kind of this really large positive bubble next to a very small negative. Of course, that's only one. The other one would be if I flip the P around. So I have the plus and the minus. Now we're going to go from the other direction. So the other one is going to essentially have two of these. So when I reinforce them, or when I kind of put them together, what you end up with is something that looks like this. Here's my positive, and then the same thing on the other side. Negative and positive. So what do we notice that we have? Again, how many total things do I have? I have two. They are 180 degrees apart. 180 degrees apart. This is the combination. We call these two sp hybrid orbitals, but that's good. When we have sp hybridization, notice that we are linear, because we're combining s, which is omnidirectional, and p, which is one direction. I guess omnidirectional means one direction. Anyway, px and s does not have a direction. P does have an orientation. So same question here. What happens if I overlay an S, the px, and the py? And now all of these are going to be overlaid together again. So if I get if I'm combining 3 atomic orbitals, I'm going to get 3 hybrid orbitals out. Okay, so when I overlay these, let's think about what this looks like. So it's going to get messy, but that's fine. Here's my S. Here's my P. And here's my Y. So a couple of things that we have to consider. Things that we have to consider is this is in 2 dimensions. So that means that our hybrid orbitals will only be in 2 dimensions. And in fact, that's exactly what we get. So we get 3 of those same type of looking hybrid orbitals. This is sp2 hybridization. And what you end up with is (120 degrees apart. And they kind of have this trigonoplanar look because this is sp2 hybridization. So same thing here. Again, when you finish combining these p and s orbitals, I'm going to stop writing the little bulbs on the other side because generally we don't talk about those. Now we're in 3 dimensions because I'm combining the S, PX, PY, PZ to give me the tetrahedral. Again, the idea is I'm combining 4 orbitals, I'm getting 4 orbitals out. This is sp3. So the overall shape is the important thing, but what we're seeing is it's predicting the VSEPR shape. VSEPR is giving us exactly what we need. So what would you predict for the overlap of 1s, 3p's, and 1d? So we'll give that a go. How about the d2? So again, hybrid orbitals can be a combination of all of those. And that's kind of the point. So when we actually trying to determine the number of bonds, we always generally start, for VB theory, we always start with a Lewis structure, believe it or not, because the Lewis structure is going to kind of guide us to the more proper will lead us to the proper hybridization. So in the ground state, how many bonds can an atom form? And I know I did this with one class, but I'll do it with you all now. So this is carbon in its ground state. Again, this is energy. So the higher the 2p is higher in energy. So right now we can form 2 bonds, right? But we know that hydrogen likes to form 4 bonds. So that doesn't make a whole lot of sense. So what we're going to do is, let's see how many we can make when we excite carbon. So let's take carbon and let's excite it. I'm going to take 1 electron. I'm going to take this red electron here and I'm going to promote it to a higher level. Okay, so there we go. So now we have 4 potential bonds. So in its ground state, it can have 2. In its excited state, when I promote one of those electrons, it can form 4. But the only issue we have to think about here is these bonds, we're going to have 3 that are the same and 1 that's different. But what we do know about how carbon forms bonds is we see the exact same thing every single time. And so that's why we shift to the idea of hybridization. So I have a carbon in a hybrid sense. I'm going to hybridize these orbitals by essentially combining the 1s and the 3 p's to give me 4x sp3 hybridized orbitals. So this is a degenerate state. Notice that the energy is below a p but above an s. Degenerate, again, what that means is same energy. So they're all the same energy. They're all going to be bonding the exact same. So if that's my centralized carbon, here is my central carbon that I've just created. There's my hybridized carbon that I've just created, each with 1 electron in it. And now I'm going to bond it with, let's say, hydrogen. There's my hydrogen with spin down, hydrogen with spin down. In the back, we have another hydrogen with spin down, hydrogen with spin down. And that's exactly what we see. We see that sp3 hybridized orbital because we've combined 4 of these to give us this shape. Okay, so again, that idea of we know we're going to hybridize to form those. By the way, when we hybridize, we're going to take all of these because I need to form 4 bonds. I need to form 4 bonds. I can form 4 bonds. I don't know why this shifted, but it's fine. Let's use it. So in its ground state, how many bonds can boron form? Okay, so boron, 1, 2, 1, 2, 3. So it can form 1 bond because it has this 1 electron here. Okay, now let's excite it. Boron in its excited state. And then we're going to hybridize it. Now I only want to hybridize the ones I want to form bonds with. So those right here, by combining those, I'm combining 1s and 2 p's to give me 3 sp2 hybridized orbitals. By the way, this p is still sitting out here. And we can form 3 bonds that look the exact same when we have hybridized orbitals. And that's exactly what we do. And we're going to combine these with chlorines, but remember the chlorines are going to be bonding through their p orbitals. So there we go, spin down. There's another chlorine. Spin down. Spin down. There's my 3rd chlorine to give me BCl3. Okay, so why don't you guys give this one a try? Beryllium fluoride. So create the hybridization. It's actually already right there. So again, to predict hybridization, we're going to draw the Lewis structure, which we're good at. We're going to use VSEPR to determine how many domains or the hybridization we expect to see on that central atom. And then we're going to specify the hybrid orbitals needed. See table on page 2. It's way above. So we don't actually really have to worry about that. So specify the hybrid orbitals needed, but we can do those calculations based on, this thing here, SPE, to determine what type of hybrid orbitals that we're actually going to need. The bond angle between hydrogens is a little less than 109. what can be concluded about the nitrogen atom? Draw the orbital level diagram. So let's hybridize this. Let's hybridize water. And let's move on to looking at multiple bonds. So give those a try. We're going to go over those in class. There are two types of bonds. A sigma bond is, this is the important part here, our end-to-end overlap. It's important to recognize that a sigma bond, the first bond is always sigma. We call it a sigma bond because it is end-to-end. You're going to see they're going to be facing one another, okay? In fact, there's only one sigma bond. The rest have to be known as what we call pi bonds, where it's going to be a side-to-side interaction. So yes, so side-to-side versus overlap. So if I take a look at oxygen, okay, so if I have oxygen, 1, 2, 2, there we go. So in this case, I have 2 p orbitals for bonding. So what does this bond actually look like? Well, first of all, one of them, if we actually look at these, I'm going to put them together here. So I'm just going to take a quick pause, and I know that I'm drawing these kind of elongated lobes, but in actuality, these things really kind of look like this. Okay, I'll put that there actually. They kind of look like this, negative, positive, but it's easier to draw them as elongated. So here is my oxygen, okay, and here's the oxygen next to it. Those px orbitals are lining up to one another. Positive, positive, negative, negative. So you can imagine the end-to-end overlap is if I take this other oxygen and I bring it close together, and that's what we have. So end-to-end overlap, that is right there. That is my sigma bond. There's my oxygen. Those 2 electrons from one of these, let's say this one, overlap. This right here is my sigma bond. Okay, all right. All right, so that's my sigma bond that I've formed between the 2. But we also have one other possible interaction, and this is going to be a pi bond. A pi bond is going to be a side-by-side interaction, side-by-side orbital overlap. And so we're going to take a look at this a little bit separately. So if I kept going, and in fact, I'm going to copy this and use this. If I ignore the sigma bond, because they're there doing their thing, so I'm going to just kind of ignore the sigma bond, okay? In fact, I'm just going to replace it with a plane. There we go. So this right here is my sigma bond, because it's going to be easier to see if I do it this way. So if I take this, how am I going to do this here? Let me just try this way. And now I take let's get it in position. So now I take the other orbital that I have. So it was here, right? And so we have the sigma bond. We're going to have a side-to-side interaction. This interaction here, notice the overlap on the top and the bottom. In fact, I'm just going to put that there. This is my sigma in between here. This interaction is going to be those 2 together are going to be the pi bond, where you have the overlap from the side to side from those top 2. Okay, so up here, essentially we have the overlap here, which counts as the pi bond. Both of those together. So the positive on top is interacting and the negative on the bottom is interacting. In fact, what this actually looks like, again, if that's my sigma bond, after they overlap, what you have is a plus above and a minus below. This right here is my sigma bond. So side-to-side interaction. Anything beyond the first is going to be sigma bonding, okay? So a single bond is 1 sigma. A double bond is 1 sigma and 1 pi. A triple bond would be 1 sigma and 2 pi. And this is going to be the important portion to really understand. First one is always sigma. Anything beyond the first is going to be a pi bond. Okay. All right. So with that said, what is the using predict the geometry? Let's take a look at the hybridization of the central carbon, and let's figure out what this looks like in terms of its bonding overlap. And we're going to take a look at all of this. Okay. And so this was C2H4. We're going to take a look at C2H2. And then we're going to talk about delocalized, and we're going to talk about all of this in class. Beyond this, we would talk about MO theory. MO theory is much more useful in a number of ways, but it's also less easy to see and it's much harder. So I don't think we're going to cover it, but MO theory is something to look into. So yeah, so we're going to do the rest of these in class, but that's a good place to stop.